Now that we have clarified what makes an approach systemic, we can turn to the questions of how system thinking is applied in practice. If food systems are made of interacting elements, feedback loops, and nonlinear dynamics, researchers need ways of making this relationship visible and analyzable. This second unit therefore introduces some of the main tools used to represent system dynamics and shows how they can help us to understand feedbacks, lock-ins, and possible pathways of change. To put systems thinking into practice, it is important to keep in mind that there are different families of system approaches. Some approaches, such as system analysis, operational research, and system dynamics, rely more strongly on formal modeling and are often used to simulate behavior, compare interventions, or explore scenarios. Others, such as soft systems methodology, are more qualitative and interpretive and are used to make sense of complex situations, reveal differing stakeholder perspectives, and support learning about possible course of action. In addition, critical system approaches emphasize that any systemic inquiry also involves boundary judgment and normative choices, and therefore requires reflection on what is included, excluded, and treated as relevant. Across these approaches, system thinking may help identify interdependency, feedback processes, lock-ins, and leverage points. But different methodologies do so in different ways. System approaches. Feedback loops are an element of interest, as they are key for understanding the development trajectory of the overall system. These loops can be of two kinds. They may be positive feedback loops, which leads to an amplification of the problem, or negative feedback loops, which leads to a stabilization and possibly to the eventual disappearing of the problem. A first example of a positive feedback loop is the phenomenon of market concentration. Among the actors in agricultural systems, some actors become larger. These actors benefit from lower costs and also acquire greater influence over the system. They therefore become dominant in the market and make market access more difficult for the smaller actors, who do not benefit from the same economies of scale or influence effects. Ultimately, the smaller actors are absorbed by the larger ones, which then become even larger. This phenomenon has been studied by Wesley and Benton in a recent report for the United Nations Environment Programme. It shows that around the actors of agricultural and food systems, whether upstream, seed, synthetic chemical inputs or mechanization, or downstream, traders, processors, or retailers, a process of concentration can be observed. Another type of loop is the negative feedback loop. In this case, it leads to stabilization. For example, when the impacts on biodiversity and pollution increase, citizens and consumers become more aware. They then tend to consume more organic product and support more sustainable production systems. As a result, more farmers shift and convert to these new models, which in turn leads to a reduction in biodiversity loss and pollution. Within a system, we can spot multiple such loops. which often also interact by working on the same components. The result is a causal loop diagram, which represents the mental model capturing the relationships between dependent and independent variables, including all the feedback loops. This may take the form of positive feedback loops, leading to escalation or exponential growth, or the form of negative feedback loops, leading to stabilization of the system. Sometimes a system appears to stabilize in a situation that is taken to be unsustainable or undesirable. This is often the case for contemporary food systems. Transition scholars call this a lock-in.
But what are lock-ins? In Emphasis, the concept of lock-in is built on two definitions. On the one hand, there are barriers, which are concrete and specific obstacles that actors face to change their ways. And on the other hand, we have lock-ins, which emerge out of the interaction of multiple barriers. Let us take the case, for example, of the development of organic farming in Flanders. We would agree that some of the barriers faced by farmers to switch to organic farming are the intense competition for farmland and labor, the dominance of an agri-industrial mindset, competition for consumers, and the fact that conventional systems remain more profitable. However, when looking more closely, we find that these individual barriers interact with one another, accumulate and create complex situations in which the system develops resistance to change. And this is where the concept of lock-in comes in. It refers to a specific configuration of these barriers that result in the system being blocked or locked in. And it can be useful to represent these lock-ins in the form of a system diagram. This earlier representation of barriers to organic farming can be integrated into a more systemic approach by showing interactions among the different elements. This model represents the links between competition for labor and land, agro-industrialization, competition for consumers, and the overall profitability of conventional farming. The loop on top captures how competition for land and seasonal farm labor intensifies pressures for scale enlargement and intensification in conventional production systems. Agro-industrialization makes it possible to cope with that, which in turn improves the profitability of conventional organic farms, and that in turn deepens the scramble for scarce land and seasonal labor. The loop below shows competition for customers. This competition pushes actors to double down on agro-industrial practices, like reliable uniform supply and making savings on costs and logistics. This further strengthens their competitive position and, through overproduction relative to current demand levels, keeps customer competition high. Together, these strands form a self-reinforcing dynamic that privileges capital and scale-intensive production systems. And this is what we call a lock-in. It is an emerging property of the system itself. It arises from the interactions among different barriers. So the key point is this: the system is not stuck because nothing is happening. It is stuck because the forces that shape it keep pushing in the same direction. This also means that solving one problem in isolation is often not enough. Even if you improve advice for organic farmers or raise consumer awareness, other pressures may still hold the system in place. This is why system thinking is useful. It helps us see how separate problems connect and why change can remain so difficult. Beyond providing these really important qualitative insights, the system approach also makes it possible to quantify and build scenarios around key dimensions. Take, for example, the share of organic food in our diets. If you want to meet the demand for organic vegetables, there are two main options. You can either import organic vegetables, which will then compete with the locally produced vegetables, or we can increase the area devoted to organic vegetables for production locally. This dynamic depends largely on the economic attractiveness of local production. This attractiveness can increase with growing demand for organic products, and it can decrease when competition from imports becomes considerable. So what we observe here are feedback loops, a reinforcing loop supporting local supply development, and a balancing loop, which can weaken it. This is how the situation can be described using a causal loop diagram. We can now represent the same situation using a stock and flow perspective. The interest of the stock and flow approach is to allow quantitative modeling informing the dynamics of variables such as the level of organic vegetable production in relation to demand from local consumers. We can define one stock as the area under organic vegetable production and another stock as the availability of organic vegetables for local consumers. These two stocks are complementary, but their evolution depends on the local production potential and the contribution of imports. This model represents the competition between two supply models, local production and imports in relation to overall availability to consumers. By representing these elements as stock and flows, we move from a qualitative causal logic to a quantitative framework. This unit has shown that systems thinking is not only a conceptual perspective, but also a practical way of representing complex dynamics. By making interactions, feedbacks, and lock-ins visible, systems tools help us move beyond a list of factors towards a more dynamic understanding of food systems. But once we begin to represent systems in this way, another challenge becomes clear. Food systems operate across multiple scales and involve many different kinds of knowledge. This is the focus of the next unit.